This video is going to teach you about velocity, how to draw a velocity vector, how to get a velocity vector in component form, and also how to extract information about the velocity vector from a position versus time graph. So first, let's talk about what velocity is. The symbol for velocity that you'll see in equations and read about in your physics books is just the lowercase letter v with a vector symbol on top of it to show that it's a vector. It has units of length divided by time. The standard SI unit would be meters per second. And I would describe velocity as a vector that describes the change in position with respect to time. So position is also a vector, so technically it's a vector that describes the change in the position vector with respect to time. So if your position is changing, then you have a velocity that's not zero. If your position isn't changing, if you're sitting still, then you have zero velocity. Another common way of describing velocity, or the norm of velocity, is the word speed. So speed is a common word that people use. And I mean, you have a speedometer on your car, you see speed limit signs on the highway. It's describing the norm of your velocity is called your speed. To calculate velocity, you're going to need a couple of equations. Just remember overall that velocity describes a change in a position divided by a change in time. So first you need to identify your initial position and your final position. And this initial and final is describing a time interval, the initial start of the time interval and the final or end point of the time interval. So identify your initial position and your final position, and identify your time interval. And that's really all you need in order to calculate velocity. So the equations for velocity, there's a few of them. I'm going to start off with the equation for something called average velocity. In this case, the time interval that you're considering is a finite time period. Like you can identify the start and the end. And you would use this equation here that it's r final minus r initial, those are both vectors, divided by t final minus t initial, where time is a scalar. Time has a direction that is never changing. Time must go forward. So when you're considering these time intervals, they're always positive. T final is always bigger than t initial. We can't travel backwards in time yet, so your time periods or these time intervals will always be positive. Keep that in mind. You'll see here in this equation, this is another common way of writing the average velocity as delta r, where that delta is a Greek symbol that means change. So you might see either one of these equations, but they mean the exact same thing. Another type of velocity is called instantaneous velocity. And this is the case where the time interval is infinitesimally small. So it's no longer finite, it's infinitesimally small. To calculate instantaneous velocity using this equation, obviously you're going to have to use calculus. That's a derivative there. So velocity is the derivative of a position vector with respect to time. So I know right now some of you may not know calculus or ever plan to use calculus. We're not going to use it in this course. I'm going to give you some other tricks in order to find instantaneous velocity, but I do want you to be aware of what instantaneous velocity is based on this equation, because if you are going to take calculus-based physics, you'll use that equation over and over and over again. So like I was saying, when the time interval becomes infinitesimally small, average velocity and instantaneous velocity become equal to each other. So if you can make your time interval small enough, you can actually calculate instantaneous velocity without doing any calculus. So let's do a quick example here. Let's find the direction of a velocity vector based on these two position vectors. So here's my initial position vector and my final position vector. I know these two locations. This is where I started and here's where I ended. So now let's draw the displacement vector. This is the change in position. Here is my displacement vector delta r. And if you look at our equation for average velocity or even for instantaneous velocity, it's that delta r vector divided by time. If you're dividing a vector by a positive scalar, you might be changing the magnitude of that vector, but you're not changing the direction. So the direction of the velocity vector is equal to the direction of the delta r vector. So if you know the displacement, you automatically know the direction of the velocity vector. Let's do another example where let's do it in component form now. That was kind of a graphical way of determining the direction. Now let's do some stuff in component form. I have a dog that's sitting near a rock and then he moves to a tree. It takes him 10 seconds to do this. So our delta t in this problem is 10 seconds. I drew the vectors in like graphical form. You see them as arrows. I'm going to go ahead and I've already put them into component form on my own time. So if you would like some practice putting vectors into component form, I would pause the video right here and practice putting these two vectors into component form and check your answers with mine. Now I'm going to calculate the average velocity vector for the dog. So average velocity is our final minus our initial divided by delta t. So let's plug in these expressions that I have in component form. Our final was -8 meters y hat. Sorry, that should be x hat. I did that wrong. That should be an x hat right there. Okay, so that's our final. And then minus the r initial. So 0.779 meters x hat minus 2.9 meters y hat. And all of that is divided by 10 seconds. So V average. If you do a little bit of arithmetic here, make sure that you only combine x hat terms with x hat terms. I have -8 minus 0.779. So that's -8.779 meters. I'm going to do divided by 10 seconds, x hat, plus, because I had minus a negative, so plus 2.9 meters y hat divided by 10 seconds. So I just distributed that denominator to both of them. And so this is how I'll get my final velocity as -0.8779 meters per second x hat plus 0.290 meters per second y hat. And that's my final answer for the average velocity during this time period when the dog was walking from the rock to the tree. All right. Another really important concept here that I need you to understand is how to extract information about a velocity vector from a position versus time graph. So I'm going to introduce this to you in a way I think you can relate to. Imagine that you're playing like a Mario Kart and you're watching a race. All right. So you're racing your friends. There's 4 players that are doing a race. It's a kind of a boring race. They're on a horizontal track, 10 meters long. So it's just a straight line. And I am going to record their positions as a function of time while they're in this race. And I am now going to graph the scalar component of their position in the x direction on a graph. So I'm only graphing this x component, but honestly, they're only moving in the x direction. So what I'm graphing is really the norm of the position of these players during this race. Okay, so here's my graph here that's showing their positions as a function of time. You can see on this graph here who won the race, who got to the finish line first. Peach got there in a little over 3 seconds. Mario got there in about 5 seconds. Bowser took about 6.5 seconds, and Yoshi took full 10 seconds. So you can see who won the race. You can get an idea of what happened in their motion. I want to ask the question, what was Mario's average velocity during the time interval from 2 seconds to 3 seconds? So I'll remind you again, here's the equation for average velocity. In order to use this equation, I need to identify his position vector initial and his position vector final. So initial time is going to be 2 seconds and final time is 3 seconds. So I'm just going to label these on the graphs. I'm going to identify Mario because I was being asked about Mario. So I'm going to look at the blue line from 2 seconds to 3 seconds. So to use this equation here, his final velocity vector is at 3 seconds. He was at 6 meters. All of this is in the x hat direction, minus his initial position at 2 seconds, which is 4 meters in the x hat direction, divided by t final minus t initial. So 3 seconds minus 2 seconds. And so overall, I get 2 meters x hat divided by 1 second. So that's 2 meters per second x hat. That was his average velocity during that particular time period. The next question asks, though, did his velocity change at all during the race? Like if I had asked you from maybe the time period from 4 seconds to 5 seconds, would you calculate the same velocity? If you'll notice what I'm doing here, when I plugged into this equation, do you see how the numerator of my fraction is calculating the change in the y quantity? and the denominator of my fraction is calculating a change in the x quantity. There's a parameter when you look at a graph that describes this exact thing. It's called slope. Slope describes the change in y divided by the change in x. So if you look at my graph here, Mario and even all the other players, their positions are described by lines. A line has a constant slope. So anywhere where I try to calculate his velocity from this position versus time graph, I'm going to get the same answer because his position is linear. And so I would say no, his velocity didn't change the whole time. It was constant because his graph is linear. So here's the information that you need to get about how to extract velocity information from a position versus time graph. It's all about the slope. You really got to focus on the slope of the position versus time graph. That's how you can calculate instantaneous velocity. I calculated that. You can also calculate average velocity like I did on that last graph. But I think the more important thing here is that you can calculate instantaneous velocity without actually using calculus. You can use the graph and the features on the graph to get this instantaneous velocity. So just remember, lines have a constant slope. So if your graph is linear during some time interval that you're investigating, then that graph is going to have a constant slope. And you can just use the equation for slope to calculate that velocity. If your graph has curvature, though, then that means that the slope is changing, which means that the velocity is changing. So you need to be a little bit more careful. You can't calculate the slope of a curve. What you can do, though, is calculate the instantaneous slope of that curve at one instant in time. So let's do an example here. Here is a graph that shows the scalar x component of the position vector as a function of time. And let's say that I want to investigate the instantaneous velocity of this vector at a few different time periods. Let's look at it here at 2 seconds. In order to get the instantaneous slope, I have to draw a tangent line at 2 seconds. So I do my best to draw a line that skims the graph right at 2 seconds and nowhere else. So this would be my instantaneous, or this is my tangent line at t equals 2 seconds. Let's say I was being asked at 5 seconds, right there at like the apex of my curve. If I draw a tangent line there, that tangent line is like a horizontal line because I'm right at the peak of my parabola. Maybe if I'm being asked about this one over here at like, let's say 11 seconds. And this tangent line looks something like this. And so now that you have lines, now you can calculate the slopes of those lines. So that's how you can get instantaneous velocity from a position versus time graph without really doing calculus. You're using tangent lines instead. And of course, you're a human, you're not a computer, so your tangent lines won't be perfect. But if you're careful, you should be able to get in the ballpark of what that number should be. So another way to extract information from these graphs, notice that each of these graphs describes the scalar component of position in a different direction. So here's the x direction, y direction, and z direction. To really understand the full motion of your object, you need a position versus time graph for every dimension of space, because each of these is just giving you the scalar component in that direction. So if you're working in three-dimensional space, you need 3 position versus time graphs to really understand the motion of this object. So let's use these graphs and let's write down, first of all, the position vector of our object at t equals 5 seconds. So I'm going to mark on each of these graphs t equals 5 seconds. And the position vector, I can just get this as the data straight out of the graph. So the position vector is the scalar component in the x direction times x hat. So the scalar component, I would say, is about 2.5 meters x hat. In the y direction, it's right here on 6 meters y hat. And in the z direction, it's right going through the x-axis, so that's 0 meters z hat. All right, position vector is easy to get from a position graph. A little bit more thinking is required to get this instantaneous velocity vector. Remember, the instantaneous velocity is given by a tangent line, the slope of a tangent line to the graph at that point in time. So this time I'm going to draw my tangent lines. And really the only one that I need to draw it for is that one that has curvature to it. You can also draw it for the linear ones, but you're really just reproducing the line, so it doesn't matter. So if I look at these purple tangent lines that I drew on each of my graphs, the slope of that tangent line tells me the velocity. If we look at the x graph, the slope of that tangent line is 0 because it's a horizontal line. So I would say 0 meters per second x hat. Now look at the y graph. Again, my tangent line is horizontal. So that's again 0 meters per second y hat. The slope of the tangent line tells you the velocity. Now if I look at the z direction, now my tangent line finally has some non-zero slope. So I just need to calculate the slope of that line. So I'm just going to choose 2 points off the line. I'm going to choose 0, 10, and 5, 0. So I choose 2 points on the line and I plug it into the slope equation. So the slope would be 10 minus 0 divided by 0 minus 5. And so I get -2 meters per second. And so that gives me my final answer for my instantaneous velocity vector in component form. And I got that straight out of these graphs. So as one little last exercise here, let's look at this graph. Let's say we are replaying our game and we're going to let our racers go again. And let's see this time, let's analyze their motion. Something very interesting happened here. There's a lot, their graphs are not just nice, straight, pretty lines. There's a lot of different curvature and stuff going on. So let's analyze this graph and try to answer the question. Let's try to rank the magnitudes of the player's instantaneous velocity at t equals 6.5 seconds. So we're going to identify on the graph, we're going to go to 6.5 seconds, something like that. And now let's investigate the slope of each of these graphs at that point in time. The slope is going to tell us about the instantaneous velocity. So who has the steepest slope? Whoever has the steepest slope is going to have the biggest instantaneous velocity. And be careful, they did mention here it's the magnitude of the player's instantaneous velocity. And so we're kind of taking like the absolute value of the slope. So if you look at the graph here, Bowser actually has a negative slope, that green line, he's sloping downwards. And so his velocity is negative, but I'm only concerned about the magnitude of it. So don't worry about it being negative. I would say if I look at this graph here, I think that Bowser and Yoshi, I think they have the same slope. One's positive and one's negative, but I think that they are equally steep. And so I think Bowser and Yoshi are tied at that moment in time for the steepest slope. So this is the biggest number up here, and here's the smallest one down here. All right, now let's focus on Mario and Peach. I actually can't even see Peach's graph. I'm going to kind of interpolate and think that maybe her graph looks something like that. If I look between Peach and Mario, if I draw that instantaneous tangent line and get the instantaneous slope of that line, I would say that Mario's line is definitely steeper than Peach's. So I'm going to put Mario in the middle. And Peach is actually, she has the slowest speed at that moment. She already won the race, so maybe she just didn't care. That's why her speed is so much slower. But that's how I would rank the instantaneous velocity of each of these players at that one instant in time. All right, and so now I think you have everything you need to know, at least for this course, about velocity vectors.